Okay, another graphing example here. Now, the thing about this one is we finally back to a rational function. The one we did a second ago was, or in the other video, was a polynomial. So now onto a rational function. Now, this isn't a full-fledged rational. It doesn't have all the pieces yet, but it'll give you a feel for how rational functions go. So I'm going to try and follow the same steps so you get used to the steps. And hopefully you'll see after seeing 3 or 4 of these that the steps sort of follow the same pattern every time, and we'll try and get that down to an acronym before we get too far. One thing we should do right away is just see if this thing can factor. And this time I put factor question mark because there's nothing to factor about this one. But I think you'll find your life easier if you go ahead and get a factored version of these right off the hop. So our first move is to check for domain issues. So we want to know when x squared plus 1 is equal to 0, when that denominator is equal to 0. Later on, we'll have to watch out for negative square roots as well. But for now, all we've got is the denominator to worry about here. So x squared plus 1 equals 0. And there's 2 ways to see that this isn't going to ever equal 0. One is to look and go, well, x squared is always going to be at least 0. And if we add 1, that's going to be above 0. So you can see it directly. It could be that you actually do take the steps and move this over and go x equals plus or minus square root of negative 1. And so we see there's no domain issues. We can't do the square root of negative 1 in the real number system, so we don't have to worry with that. Okay, so no domain issues. Even though there was a denominator, there's no domain issues. So that's something to take note of, is that just because you see a denominator doesn't mean there has to be domain issues. You have to go through those steps. Now, intercepts will be the next step we'll do each time. And I always do y-intercept first because it's a little bit easier sometimes. So for y-intercept, set x equals 0. So I get y equals, 0 on the top and 1 on the bottom. So I get a y-intercept of 0. And then for x-intercept, set y equals 0, so I get 0, oops, missing an equal sign up there, I just noticed that. 0 equals 5x, and so I get x equals 0. Not interesting in the sense that I didn't get any extra x-intercepts here. I just got that same intercept I got, so there's a point at the origin. I'll graph that later. Now, asymptotes. This will heat up as the examples get more and more complicated. And basically for asymptotes, we want to look at 2 different things. We want to look at vertical asymptotes. But because there's no domain issues to worry about, there's no times where the denominator equals 0. We found that out earlier, that there's no vertical asymptotes here. And if you're wondering more about vertical asymptotes, don't worry. The next example we do in the next video deals with those a little more directly. Next, horizontal or oblique asymptotes. And this is where you have to remember all those rules about the degrees. So here, the degree of the denominator is greater than the degree of the numerator. And when that happens, we have a vertical asymptote, or sorry, a horizontal asymptote. Of y equals 0. Now, there's several ways to get to that. In other lessons, sometimes we've multiplied everything by the 1 over the biggest x power and sent the limit as x goes to infinity. But you can also memorize the 3 rules about asymptotes. Then the first of those rules is if the degree on the denominator is greater, you get a horizontal asymptote at y equals 0. If the degrees are equal, then you take the ratio of the top coefficients. And if the degree on the top is higher by 1, you get an oblique asymptote. If it's higher by more than that, you wouldn't get any asymptotes at all. So those are all those rules very quickly reviewed for you. But in this case, I only got to worry about the horizontal asymptote of y equals 0. Next, intervals. I'm going to go up here where I get a little more space. Intervals of increase and decrease. I want to note that this is the first of the calculus moves. All that stuff over here, domain, intercepts, and asymptotes, that was all stuff straight from advanced functions. So now we're going to need the derivative. Here we go. F prime, derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. some simplifying here. Some more simplifying here. And that is the derivative. Now, to do what we want to do next, though, it's very convenient to put it into factored form. So I'm going to go f prime at x equals negative 5 x squared minus 1. I'm just doing the common factoring that I see there. And then one more step. That's a difference of squares. So I get x plus 1, x minus 1. And so, for max mins, set f prime at x equal to 0. Sometimes we phrase that for critical numbers, set f prime at x equal to 0. So sometimes we phrase it that the other way. And here we're only worried about the numerator. And so we can see the numerator directly. I'm going to write it out, but you can pick that right off because I put that in factored form. I get critical numbers. So I'm going to use both phrasings here. Critical numbers of x equals negative 1, x equals positive 1, okay? So those are the things I'm going to need for my chart. Well, I'm also going to need any domain issues for my chart. But notice that just like above, there's no domain issues for the derivative here. X squared plus 1 can never equal 0. But we do mention that here because if you are building one of these charts, you want to get where the derivative is 0, but also where you get potential discontinuities and problems with the derivative, like where the derivative can't be taken. So down here, I'm going to continue on with that. I'm going to say, okay, I got to build my chart. X less than negative 1, between negative 1 and 1, and x greater than 1. These are the intervals that I want to check to see what's going on with the derivative. And the derivative is negative, it's a big one, negative 5. And the numerator, I had x plus 1, x minus 1. And on the bottom, x squared plus 1 squared. Those are all the factors. And when you want to build one of these positive-negative charts, you want to have all those numbers in there. I'm going to sort of do this slowly because there's a lot going on here. So for a test value, I'm going to check for x less than negative 1, I'm going to use negative 5. Between negative 1 and 1, I'm going to use 0. And for x greater than 1, I'm going to use 5. There's lots of choices there. Those are the ones I happen to choose. So slowly through this. If x is negative 1, that leading factor of negative 5 is still negative. That negative 5 plus 1 will be negative. Negative 5 minus 1 will be negative. And that bottom is squared, so it doesn't matter what I put into there. It's squared. It's going to come out to be positive. And when I go negative times negative times negative divided by a positive, that whole section is going to come out to be negative. That means it's decreasing in this part of the graph. Subbing in 0 in there, the negative 5 is still going to be negative. Then I get a positive and a negative and a positive as I put that 0 into each of the factors. And here I get positive, so we're talking about an increasing function in there. And then if I put a positive 5 in there, that negative 5 is still going to be negative. And then I get a positive, and the bottom's always positive, so I get negative here. So I get decreasing. So you're just taking those test numbers and putting them into each of the factors there. So what's the end result? The end result is I get a minimum at negative 1 comma something, and then I get a maximum at 1 comma something. And then your job, I'll leave that as an exercise, you can practice your subbing, is take the negative 1 and positive 1, get your calculator out, and put those back into the original function way up here. Put that in there to get the y values that go with those x values. So when you want y values, you got to go back to the original function because that's where we get y values. If you sub those in there, you should get negative 2.5 for this y value and positive 2.5 for this y value. Okay, so that's the intervals of increase and decrease and max mins all reviewed there. And the last thing we want to do now, just learn this chapter, concavity. And here we're going to need the double derivative. Now, choosing which one to use to do the double derivative, see the factored form is a big mess. All these factored forms are a big mess. So all I'm going to do is sort of point at this one and say, hey, that's the one we probably want to use to take double derivatives. So let me just copy that thing down here. F prime at x, the numerator was negative 5x squared minus 5. See, that's a little easier to work with in non-factored form. See, sometimes we like the factored form if we're trying to solve it, but if we're trying to take the derivative, we much prefer the non-factored form. And then this denominator, ooh, sort of a mess, x squared plus 1 squared. I could expand it out, but I'm not going to. I'm going to show how to handle it, not expand it out. So you get a little experience with, dealing with the non-factored version. Basically, if I have the non-factored version, I'll use it, but I'm not going to expand things out because I have chain rule available if I need it. Okay, so here we go. Double derivative coming up. Reasonable speed. Derivative of the top, negative 10x, times the bottom, what a big mess, x squared plus 1 squared, minus the derivative of the bottom, so here comes chain rule, 2 bracket x squared plus 1 times the derivative of the inside, which is a 2x. That's the derivative of the bottom. I had to do chain rule there. I wrote the exponent down and then reduced that bracket by 1 and then derivative of the inside. And then that's derivative of the bottom times the top. Now that's a big mess. Oh, over the bottom squared. So this becomes power of 4 down there. That top's a big mess. So the steps I suggest when dealing with a nasty derivative like this, I call this a half step, where I just clean up monomials so I can get the best common factor available. And so there wasn't any monomial to collect in that first term in the numerator. But in the second term, I can tidy this up and make it a negative 4x and then an x squared plus 1. Ooh. And the negative 5x squared plus 5. Awfully tempting to common factor that negative 5 out as the monomial. But you don't have to. So if you like that step, if you like taking out a common factor of that thing, then I like it too. But I'm not going to here because I'm going to stick to my sort of pattern, which is to just deal with monomials that are in there. So I've done that there. And so now the common factor step, and I'm going to try and use some color coding here to make this clear. What I'm up to here is that I'm going to switch over to like an orange and go, okay, the common factor here, I see a negative 10x and a negative 4x, so I'm going to common factor out a negative 2x. And then I see this x squared plus 1. It's squared in the first bracket, but there's only the 1 in the second bracket, so I'm going to factor out x squared plus 1 in the second bracket. So there's the common factor. And that just tidies things up a whole lot. Now, me personally, I like using squared brackets. As soon as I use a common factor, it helps me to stay a little more organized inside and be able to see what's going on inside the brackets. So I've taken negative 2x out of that negative 10x. That leaves a 5. And I've taken one of the x squared plus 1, so I've only got x squared plus 1. You see, that really tidies up the inside here because I've pulled that out of there. In the second bracket, I took a negative 2x out of the negative 4x, so I got a plus 2. The x squared plus 1 was factored, and I ended up with negative 5x squared minus 5 left over there. I'm going to do a couple things in this next step and keep this negative 2x, but that x squared plus 1 that's popped out, it cancels with one of the x squared plus 1s in the bottom, so the denominator is now only x squared plus 1, and that's a cubed now. And then in the bracket, lots of good things happen. We'll do it in 2 steps here. I get 5x squared plus 5 minus 10x squared minus 10. And boy, does that ever simplify up nicely. Negative 5x squared, and then way up here, this was a negative 5x squared plus 5. Little mistake there. That was a plus 5. Weirdly, I still did the right thing on the next line there. When I common factored that out, I made another mistake there, and so that fixed that. But I'm noticing that down here because this was a negative 5x squared plus 5 here. That's a negative 5x squared plus 5 there. Plus 5, plus 5, plus 10. and I get a plus 15. And, you know, awfully tempting to go and fix my video now that I made that mistake. But I got to tell you that a lot of these questions with double derivatives and so on, that's the kind of mistake you got to be able to catch. You got to be able to scan back through and find those little mistakes when they happen so that you can fix those things up. So get good at scanning through and not erasing everything right away. You go through step by step and you go, okay, well, I made a mistake there, but I can sort of fix it. Sometimes you got to erase everything, but sometimes like the little mistake I made there, you don't have to erase it all. You can just tidy it up a little bit like that. And I can do a little bit better here. I can common factor out that -5. So when I bring that -5 out, I get -2x. I'm bringing out a -5. And in the brackets, I get x squared minus 3. And so my beautiful double derivative at the end here, 10x, x squared minus 3 over x squared plus 1 cubed. Very nice. Now, and this is like when we were doing single derivatives and double derivatives before, it's like, how far do I go in cleaning this up? And that was a hard question to answer until we get to this chapter and you realize, oh, down to fully factored, so I can do this next line easily. So for points of inflection, we want f double prime to be 0. So we need 0 equals 10x bracket x squared, x squared minus 3. Let me just do a little difference of squares on that thing. You can do it other ways to get these answers here, but just to fit this into the bottom, there's my 3 values. And you could solve that slightly different. But either way, we need those 2 zeros of that x squared minus 3. You could isolate on that thing. You could quadratic formula it if you really had to. In this case, I saw that it was a difference of squares, but using roots, you know, not too bad of a root there. So that's how I get those 2 answers there. So now I'm ready to build my double derivative table. I'm hoping I have enough room right in here. So I'm going to go, I need x less than -√3, between -√3 and, whoops, and 0, between 0 and √3, and greater than √3. Those are my categories of my double derivative. So I got f double prime, and it's 10x, x squared minus 3, and x squared plus 1 cubed. So test values, well, some interesting choices here. -√3 is like -1.7. So that's always going to be like a 1.7 in there. I'm going to need that information to be thinking out these test values. So less than -7, again, I'm going to use that -5. Between -7 and 0, I'm going to use -1. Between 0 and 1.7, I'm going to use a 1. And greater than 1.7, I'll use a 5. Okay, so putting those all into my double derivative chart. 10x, so that'll be a negative. X squared minus 3, that'll be like 25 minus 3, that's a positive. And then that bottom's still always positive, so I get negative in here. And we know that's concave down. Then -1, when I put in there, I still get a negative when I multiply it by 10. -1 squared is 1 minus 3. That's negative now. That bottom's always positive, so I get positive here. Concave up. Between 0 and √3, I'm going to use a test value of 1. When I go 10 times 1, I get a positive. When I go 1 squared minus 3, I get a negative. And on the bottom, I get a positive. So that's negative, and I'm concave down it again. And then x greater than √3, so I'm using like 5. 10 times 5 is a positive. 5 squared minus 3, that's a positive, and the bottom's always positive, so I get positive there. By the way, the bottom's not always positive in every question. It's just that when it's x squared plus 1, whatever value I squared and add 1, I'm always going to get a positive. So now here I get my points of inflection here. Points of inflection, there's 3 of them. There is -√3, comma something, 0, comma something, and √3, comma something. So when I plug my -√3 in there, all the way back into the original function, I think I get like a -2.2. You can sub that in and see what you get. When I sub in 0, well, that's the 0, 0 point. I subbed that in before. And when I plug in positive √3, I get 2.2. So you can do that subbing to make sure you get the same values as me. So all that information goes into my graph. So I'm going to go back to the beginning. Whoops, not to back to the previous. Yeah, oh yeah, back up here. Back to here. And I'm going to get that weird blue color that I sort of like for graphing on this. I'm going to go through these individually. So first, intercepts. X and Y intercept, 0, 0. And I'll label these points in just a minute, but there's my 0, 0. Horizontal asymptote y equals 0. Now, you can draw this all the way across. The way I handle horizontal asymptotes, because horizontal asymptotes are just talking about end behavior. It's easy to get confused about horizontal asymptotes and draw right through them and get nervous about drawing right through them. But horizontal asymptote just means we need to end up at y equals 0. It's the end that we go out to here, and when we go out, so I don't draw it all the way across. Some people do, but it just reminds me that, hey, this is where I got to end up when it's over. Next, I found these max and mins. Where were they? -1, -2.5 was a min. So that was right about there. And then the max was 1, 2.5, right about there. So that's coming along really good. I can sort of see what's going to happen here. And then this weird location, -1.7. Let me just write that in there because I sort of need the decimal to be able to graph it. Like √3, it's hard to know exactly where that is, but when I get it as a decimal, then that sort of tells me where I'm at. So -1.7, -2.2. So -1.7, kind of -2.2. Weirdly right in about there. This is going to be tough to show the features, but I'll really try to talk it through as I do it so you can see. And then the other one, this sort of opposite point was 1.7, 2.2, right about there. Okay, so what the chart said was that it was going to be concave down from before we get to -√3. So I'm going to really exaggerate there and say, well, okay, that's concave down in there, and it approaches that asymptote. Then concave up from there all the way to 0. So it's got to curve upwards like that. Then concave down again all the way to this next point. I really tried to exaggerate that. And then concave up again in here. So I get the full shape on there. There. Much better than advanced functions because I get those max mins and I even get the shape when it's going to be curved up and curved down. So let me label a few things on here. That horizontal asymptote of y equals 0. This point 0, 0, although really you don't have to label, points that are right on the axis because it's kind of obvious what those ones are, but you should label these other points so everybody knows what they are. This was 1, 2.5. This was -1, -2.5. And I've forgotten these. Let me just make them a little bigger. With those exact values. 1.7, 2.2. And in this particular situation, those points were very symmetrical. So this was -1.7, -2.2 in there. So I get those all in there. I labeled that. Yeah, okay, that's good. All right, so that's a full graphing example. And full graphing is it has the full crazy derivatives and the concavity chart, the whole thing. What it didn't have was any vertical asymptotes to deal with. So in our next example, on the next video, you'll see one that has some nice vertical asymptotes. Okay, well, we'll see you in the next video.